When we talked about limits in a previous section, we examined the limit idea graphically. And in those circumstances, we encountered a few graphs where those graphs were discontinuous at certain positions. And I want to review that a little bit, and we want to talk about continuity in this segment. We encountered a graph that seemed to have a hole in it like this, and we said that, well, f of c is not defined because of that hole, and but the limit does exist in this circumstance. And another graph looked like this. It was kind of a disconnected type of graph, and we said, well, f of c is defined. F of c is this point, you see, but the limit at c does not exist. We don't have a limit situation as we did over there. Okay, and on this one, f of c is defined. You see the graph kind of has a hole in it, but that point is just in another position on the graph. And so f of c is defined. The limit does exist, but the limit as x approaches c, and the c is understood to be here, the limit as x approaches c of f of x is not f of c, because f of c is that point. You see, so these are situations involving discontinuity, or where the function is not continuous at a certain point. Now, it turns out that if we can remove all of these problems, then we have continuity at c. And that allows us to make a definition for a function being continuous at c. So a function is continuous at a point c if these situations occur. If f of c is defined, now notice here f of c was not defined, so this part of the definition is taking care of that circumstance. And number two, the limit as x approaches c exists. You see, the limit of the function as x approaches c exists. Here the limit did not exist. The limit as x approaches c does not exist. And the third idea is that the limit as x approaches c of f of x is f of c, and that takes care of the third circumstance that we had over here. Okay, so we have this continuous idea at c if we meet these definitions. Now, although all of these, or none of these graphs, functions are continuous at c, we can say, though, that they are continuous at other points. That is, on intervals, on this interval, for example, this graph is continuous. On an interval over here, the graph is continuous. On an interval over here, the graph is continuous, and so on. So we can find intervals over which the graphs are continuous, or the functions are continuous. And the notion of continuity over an open interval is that we meet the definition for continuity at a point for every point on the open interval. It's kind of an intuitive idea. So we meet the definition at every point on the open interval. Now, incidentally, you'll notice that in that circumstance and in this circumstance, we just kind of have a hole in the flow of the graph, and we just kind of have a break in the graph. And here we have a big break in the graph. We have the graph just seems to stop right here, and then it starts up in another spot, rather than just having a hole in it. And it's kind of important to notice that. When we have just a single hole in the graph, or we can redefine one single point, we say that the discontinuity of the graph or of the function is removable. We can remove that discontinuity by redefining just one point. Now, so here, this discontinuity is removable by defining that point to fill the hole. But here, the discontinuity is not removable because we have a disconnectedness like this. We can't just redefine a single point and have a sort of connectedness involved in the problem. So, removable or not removable. Let's look at a few graphs and a few functions and talk about, just kind of analyze what we're looking at, and talk about continuity and removable and so forth, and limits maybe a little bit. Here we have a function that's a step function. It is the greatest integer function. F of x is the greatest integer in x. And just to jumpstart your memory about this kind of function, if x's fall between 1 and 2, the greatest integer in the numbers that fall between 1 and 2, the greatest integer in those numbers is 1. You see, and then, so that's why f of 1.5 is 1. F of 1.75 is 1, the greatest integer in that number. And then when we hit 2, then the greatest integer in 2, we jump up to 2, you see. And for all the numbers in that interval, f of those values would be up here at 2. So it looks like this. And no wonder it's called a step function. Well, obviously we have a discontinuous situation for the entire function. And incidentally, when a function has like a polynomial function, has this nice flow to it and has no breaks in it and so forth, it's called everywhere continuous. And this one certainly is not everywhere continuous. So we have all of these breaks. Now, it doesn't mean that we don't have a certain kind of continuity. We have continuity within certain intervals. You see, we can define some intervals over which we have continuity. We'll say open intervals for right now. We'll talk about this open and closed business a little bit later. So the function itself is not continuous, and it is not removable. That is, we can't redefine a single point and have continuity here. In this one, this is a rational function, and in this circumstance we have a vertical asymptote. So this function is not everywhere continuous. However, and this is kind of interesting, we can say that it's continuous over its domain. You see, over its domain. Remember, the implied domain, the implicit domain, the values of x for which this function makes sense. For what values does it make sense? Well, the fraction makes sense for every value of x except for the value x being 2, because 2 causes the denominator to become 0. So the implied domain here is all real numbers except 2. And over that defined domain, we have a continuous situation because we have a continuous function from negative infinity right up to the point 2, and we have a continuous situation from 2 out to positive infinity. So it's continuous over its domain, but it is not everywhere continuous. And it's not continuous specifically at x equals 2, and it's not a removable discontinuity that we're looking at here. Here's another one. Here's one where we just have one simple hole in the problem. Notice, though, that the way the function looks algebraically, it kind of looks like we're going to be faced with a rational function. This looks like a rational function? Yeah, it's a rational function, but its graph has no vertical asymptote. We're kind of accustomed to seeing rational functions and vertical asymptotes involved in graphs. And that just isn't occurring here, and it's because this x minus 3 factor is cancelable with an x minus 3 factor in the numerator. And that's what causes the hole in the graph, is this x minus 3 in the denominator. So again, we have a situation where the domain is implied to be all real numbers except 3, because 3 would cause the denominator to become 0. So we're continuous over the domain of the function, but we're not continuous at x equals 3. This is a removable discontinuity because we can just define f of 3 to be 1, and then we would have the continuity that we're looking for, and the limit in this one exists. Here's one that's defined in pieces. The function is defined in pieces, and the graph has this appearance. And once again, we just have kind of a hole in the graph, but f of the place where the hole is defined. You see, f of 2 is defined up here. So we would say then that although the function, the entire function, is not continuous at that point, and it is incidentally continuous over an open interval over here, an open interval over there. That's all well and good. We're really concentrating our thoughts on this place where the hole is in the graph. So it's not continuous at 2. It's a removable discontinuity because we could redefine this point to be right here to fill the hole. And the limit certainly exists. The limit as x approaches 2 certainly exists in this problem. When we originally talked about limit and examined the limits of functions, we were looking graphically at the situation about an approach of as x approaches some target, then f of x approaches some value. And we were thinking in terms of right and left-hand behavior, and it's important for us to understand that here, for example, if we're talking about as x approaches 2 from the left, f of x is approaching 1. The limit as x approaches 2 from the left of f of x equals 1. You see, we know so the limit from the left at this target point is 1, and also the limit from the right of for this target point is also 1. And that means if the limit from the left is equal to the limit from the right, then the limit generally of the function is 1. On the other hand, in a situation like this, where we have this break in the action for our function, the limit from the left at that target point turns out to be 1, but the limit from the right, as we approach from the right, the limit turns out to be 2. If these are not the same, then we say the limit of f of x does not exist. Now this idea, this notion of examining limit from one side and the other, we're going to flow with that idea into continuity. We can talk about continuity from the right and from the left of certain target values. You see, we've been talking about continuity over open intervals, and we want to talk about what's required for us to have continuity over a closed interval. So here we have a situation where, in the interval from A to B, in this interval, we have a continuous function within the open interval, but not continuous, where this function is not continuous on the closed interval because of the situations that we see here. We see some holes in the situation. Well, if we close those holes, then we have continuity both on the open interval and on the closed interval, as we see illustrated in this graph. Now, for this to happen, for us to have continuity on a closed interval, we have to be talking about what happens at the endpoints, and that's what really is important. Whenever you're talking about a closed interval condition, then look at those endpoints, examine the endpoints, and that's where the trick is. So you want to look at those endpoints and verify this. You want to verify that the limit as x approaches the left end point, you see, of the closed interval, as x approaches that left end point from the right side, that limit is f of that endpoint. You see that as we approach A from the right, you see, then that limit is f of A. F of A is that point, you see, on that graph. And in a similar way, you look at the right endpoint and you examine the limit as you approach from the left side. So from the left, as we approach B from the left, you see, then that limit needs to be f of B, as we have illustrated here. So we say then that for this continuity to occur on the closed interval, we have to say that this function is continuous from the right at A, and it's continuous from the left at B. And that's what this is all about. Well, we're making this correlation. There's this correlation between limit and continuity all along, and we even see it in the properties. If we list properties of limit and continuity kind of right next to one another, we see a remarkable similarity. For example, here I'm reviewing the properties of limits. Now recall, we talked about this before in an earlier section, but if the limit as x approaches the target C of f of x is 7, and the limit of g of x as x approaches C is 4. So one limit is 7, the other is 4 for these two functions. Then the limit of 5 times f of x would be 5 times 7. 7 was the limit for f of x for that target point. And then the limit as x approaches C of the sum or difference of the functions would be the sum or difference of their limits. And then the limit of the product is the product of the limits, and the limit of the quotient is the quotient of the limits, you see. And so it just kind of flows intuitively. Well, look at the situation with continuity. It turns out that if f and g are continuous at the point C, if they are both continuous at C, then 5 times f is continuous at C. F plus or minus g is continuous at C. F times g is continuous at C, and their quotient is continuous at C. Notice I'm putting the caveat here that G of the target point is not equal to 0 to make this situation undefined. But this just points up the remarkable similarity between continuity and the limit idea. Here's a list of functions that are continuous at every point in their domain. Now, this doesn't mean that they are everywhere continuous, just they're continuous at every point that's in their domain. Polynomial functions, rational functions, radical functions, trigonometric functions. This is kind of a nice thing to know, because if you're examining for continuity and you have a weird function that is sort of the combination of 2 or 3 of these, then you can be assured that you have the continuity you're looking for by thinking of your function in parts. For example, if f of x is this function, oh, this looks weird, it doesn't fall into a category, but we can think that, okay, we have a polynomial function here minus a trigonometric function, and all of these guys are continuous, all of those guys are continuous, we're just subtracting functions, and so by the some of the rules or properties we talked about before, we know that f of x is going to be continuous. Okay, what about combining functions in another way? That is, what about the composition of functions? Well, here we have f of x as this radical function and g of x as this polynomial function, and I've calculated f of g of x, I've calculated g of f of x, and I get these for those calculations. And you know, this radical function, now both of these are continuous over their domains. The domain here would be x values greater than or equal to 3. And as long as we sort of stay away from those values of g, you see, we just can't pick a target point that's in g such that g of that target will cause us to be outside of the domain of this function, then we're fine. We're continuous everywhere in the composite functions. So basically, the composition of functions, if you're starting out with good stuff, you're going to end up with good stuff.